So before I go any further, I just want to make sure that everyone can hear me. So if you can't hear me, just use the GoToMeeting menu to raise your hand. And if you're having trouble hearing me, if my volume is not loud enough, what I'll do is I'll adjust it. Just type into the chat box and let me know. Okay, so it seems that mostly everyone has their hand raised. Once again, if you need me to speak louder or to adjust my audio, once again, just type into the chat box and I'll make sure to do that for you. Also, if you have any questions over the course of the presentation, just write them down for now and then email them to me after the presentation is done. Just in the interest of time, we won't be able to have like an in-depth sort of question and answer sort of session. But once again, your questions are more than welcome. At the conclusion of the session, just email them to me and I'll answer them individually. Okay, so let's get started. Okay, so before I go any further, just want to make sure that everyone knows that our materials are copyrighted. So, at the conclusion of this course, you'll all receive a PDF copy of all the sessions that you attended. You feel free to sort of share these PDFs with your colleagues, but if you're going to be presenting them in any sort of commercial or lecture type form, just make sure to get our permission. All right, so let's go over to today's learning objectives. So the main three objectives that we have for this course, or for this particular session, are outlined here. So first and foremost, we want everyone to gain an understanding of the theoretical principles of the limit equilibrium and the strength reduction method of slope stability analysis. So these are the two main methods of analysis that are used for slope stability by geotech engineers today. And we'll be going over sort of practical applications of each of these analysis types, as well as how each one sort of compares to the other. So sort of strengths and weaknesses of each. So yeah, that was covered in part 2. So key differences between each analysis method. And then fundamental principles of numerical modeling for slope stability. So this is something, or this particular sort of portion is what really makes these courses sort of unique, is that we'll be going over how to create numerical models of each of these analyses types. So I'm sure all of you know that the numerical modeling programs are becoming more and more prevalent in the world today, especially with geotech engineering work. So we'll go over sort of the fundamental sort of concepts of creating a model just using a software package, and I'll sort of get into detail about that in the final session, or excuse me, the final section of this presentation. Okay, once again, just a sort of a more detailed introduction to what we'll be going over. So first I'll go over some background information. So just sort of the basic concept of slope stability analysis, why it's around, and why it's something important for all geotech engineers to understand. Okay, so why do we need slope stability analysis? So slope stability analysis is used to analyze the safety of natural and man-made slopes. And here are the main design objectives of slope stability analysis. So first we want to find endangered areas. So whenever you have any sort of slope, there is sort of like potential that it could fail. And typically what you'd want to do, if you refer to the right here, is you want to find the failure surface. So the projected sort of surface upon which the slope will fail if it were to do so. And as you can see, when a slope fails, typically it has a sort of rotational sort of shape here. And what you'll do when you do your analysis is you'll simulate that. But also it can take other shapes like, for example, a block failure surface with a square cut or a wedge type failure, and I'll talk more about that in the upcoming section. So once again, also you want to find the investigation of potential failure mechanisms. So when you do your analysis, when you do your modeling, essentially what you're doing is you're simulating the conditions that would cause the slope to fail, and you want to find your factor of safety. It's something that I'll discuss later on. And the design of optimal slopes with regard to safety, reliability, and economics. So for those of you who are working with man-made slopes, what you want to do is you want to design a slope, obviously, that is not only safe but also very economical for the project demands. And you can do so using the methods that I'll show you. And then the design of remedial measures such as barriers, stabilization, etc. So sometimes certain slopes might not be able to sort of be stable on their own. So certain sort of support structures might be needed. For example, tiebacks or soil nails can be included, also geogrids, and I'll show you a couple of examples in the upcoming slides of remedial measures that can be used to stabilize your slope. Okay, so successful design of the slope requires the following data. So first you need the properties of the soil and the rock mass. So depending on sort of the material properties that you're working with, you might be able to get away with sort of steeper slopes. Or if you're working with sort of looser, less stable materials, you'd have to design for sort of softer slopes. Slope geometry, obviously the shape of your slope is, very key. Groundwater conditions. So this is another very important thing to keep in mind, that depending on, for example, if you're working in an area with high rainfall conditions, typically what you'll have to do is you'll have to create a different case, a dry case as well as a saturated case, and compare how the slope stability, or excuse me, how the factor of safety would change. And that's something, once again, that I'll go into greater detail later on, especially in the numerical modeling section. So just keep that in mind. If you're working in a very sort of high rainfall or sort of a flooding, an area that could encounter flooding, then groundwater conditions could drastically change the stability of your slope. Alternation of materials by faulting. So for example, if you're working with maybe a rock with cracks in it, or soils that have certain fault lines in them, you'll have to take that into account. So typically faulting, that'll make your slope less stable. And then joint or discontinuity system. So that sort of goes back in line with faulting. Any sort of discontinuity in the soil layers need to be accounted for in your final design. And then movement and tension in joints. So for example, if you have like a jointed rock layer, and you find that there could be sort of a significant amount of movement or tension that could cause it to crack or to fail, that's something that will have to be sort of brought up to the client, or something that had to be designed against to stabilize. Okay, and then last but not least, earthquake activity. So that's sort of self-explanatory. If you're working in a high seismic zone, you'll have to simulate seismic loading on your slope as well. Okay, so let's talk about some design applications. So here's one example of where slope stability analysis is very commonly used for embankments and earth dams. So what we have here is just a typical sort of diagram or cross-section of an earth dam. Typically you'll have an upstream side or a wet side that's sort of retaining the water, or your reservoir, and on the other side you'll have a dry side, or your downstream side. So typically when you have a sort of an earth dam, what will happen is there will be a certain amount of seepage from areas of high water pressure, the reservoir, to areas of low water pressure, which is the dry side here. And because of a certain amount of seepage that's occurring in the soil, this sort of slope on the dry side, the stability could be compromised. So typically what's done is engineers, they'll design clay cores or drainage blankets to sort of stop the seepage, or to move the seepage to sort of areas of safety. So I won't go into too much detail about sort of seepage analysis and how it relates to slope stability. I just sort of wanted to give you an introduction to it. But later on, during sort of one of the later sessions, I'll go into much greater detail about seepage analysis in general and how you can use it in coupled analysis with slope stability. So that's something to look forward to. I think it's either session 5 or 6, where we'll be going over seepage analysis in particular. Okay, so another design application would include road cuts. So if you look to the picture on the bottom left here, as you can see, this is sort of a natural man-made slope by a road. As you can see, because the slope appears to be made of sort of harder or stiffer materials, there aren't any sort of tiebacks, and it's very close to the road. So in other words, the engineers found that this slope was stable enough or safe enough to not warrant any sort of remedial measures, and it isn't designed, or it isn't made further away from the road. As you can see here to the right, though, we have another slope, which it's sort of hard to tell exactly how much bigger it is, but as you can see the machines here, that just by relativism, that the slope is very steep and very high, and because so, there's sort of tiebacks and soil nails that are being created to stabilize the slope, and obviously there's sort of a large sort of area here, just in case the slope does fail, that the materials won't sort of seep over into the road. So that's just another thing that you have to keep in mind as an engineer, that depending on the sort of project conditions you have, you might have to create certain fail-safes just in case the slope does fail. So as you can see, because the slope is very high, very steep, the engineers felt that the design required several sort of fail-safes or design precautions just in case the slope did fail. Whereas with maybe more stable materials, you don't really have to worry about those sort of precautions. So once again, road cuts would be just another example of design applications for slopes. I'm sure you've seen them around. Okay, then open pit mines are a very sort of unique design application for slope stability. So open pit mining is an open cast mining, or a surface technique of extracting rock or minerals from the earth by removal from an open pit or burrow. And as you can see, as they go deeper and deeper, what they'll do is they'll create a series of slopes that go down, as well as sort of roadways that lead down to the bottom of the mine. So open pit mines are dug on benches which describe the vertical levels of the hole. So these benches that you see here, they're usually on 4 to 60 meter intervals depending on the size of the machinery being used. But many quarries do not use benches as they are usually sort of shallow. Anyway, most walls of the pit are generally dug at an angle less than vertical to prevent and minimize damage from falling rocks. So this depends on how weathered the rocks are and the type of rock, and also how many structural weaknesses occur within the rock, such as fault, shears, joints, or foliations. So if you're working with doing slope stability with rock types, fault, shears, and joints, those are things that you really need to look out for because they can be very deceptive. I mean, if you have a fault line hidden sort of behind one of these slopes, then an excessive amount of pressure could easily crack them. So that's something, once again, that you'd have to look out for when working with rock. So in some instances, additional ground support is actually required. So for example, rock bolts or cable bolts or shotcrete are sometimes used to stabilize these slopes. So just keep in mind that those sorts of remedial measures aren't just used for open pit mines. They can also be used for the other slope types that I discussed with you before. And also, dewatering bores may be used to relieve water pressure. So, for example, what they'll do is they'll drill horizontally into the slope to take the water out. So once again, if water is being stored in your slopes, that could cause it to have a certain amount of weakness. So ideally what you'd want to do is you'd want to drain your slopes before building them. That way they'll be very stable. So for those of you who are involved in mining, I'm sure this type of slope stability analysis is familiar to you. Okay, then also we have deep excavation. So this is one of the most common types of slope stability projects that are done because, as geotech engineers, I'm sure you work a lot in foundation type projects. So naturally, when you build your foundation, you'll have to excavate the ground. So if you look to the left here, this is actually a shallow foundation, not a deep foundation. But the reason I'm showing this particular picture is just to show you the contrast between a shallow excavation and a deep excavation. So if you look to the left here, the shallow excavation, there isn't really actually much of a slope at all. It's almost sort of a 90-degree angle. So why is that? So the reason that is just because the excavation is so shallow that it's sort of negligible. I mean, you could still have a 90-degree angle such as this, and it would still be relatively safe to walk along the perimeter here. You don't really have to worry about it failing. And for example, if the rocks or the dirt were to fail, it would be very easy just to sort of excavate it further to take the dirt out. So slope stability isn't really that much of an issue when it comes to shallow foundations, is sort of the point I'm trying to make here. Whereas if you look at the picture on the right here, this is a much deeper foundation. As you can see, it's sort of like a bi-level deep foundation. There's one segment here, they sort of created a road or a support area, and then they created another level for the excavation. So this is a much deeper foundation for a much larger, much more sort of ambitious project. And look what's been done here. There's a certain amount of fencing that's been created. The slopes are there, but as you can see, it's not particularly safe to walk along this area yet, just because the slope's still being constructed. And as you can see, the excavation or the excavation lining is done, with the slope. So, the reason this is done though is just because it's not really sort of logical or very safe to have, the slope dug in or the excavation dug in at a 90-degree angle. It'd be very dangerous. And if that were to fail, there'd be large amounts of soil falling, which would take a long time to sort of fix or to clean up. So just keep in mind that, the deeper your excavations become, for those of you who have worked with, foundations for high-rise buildings or very large warehouses, I'm sure you've encountered this sort of scenario before. You had to design slopes for the excavation. So once again, that's just another design excavation for slope stability, is these large, deep excavations. And they're very key to maintain safety for a construction site, to make sure these slopes are supported, they're safe, and that the proper precautions have been taken place. Okay, then last, landfills. So this is another, sort of self-explanatory design application. Landfills are these large openings in the earth. Usually they get filled with debris or with waste before being filled up. And the slopes surrounding the landfills need to be stabilized because you don't want the landfill being filled up prior to its time. So if you look to the left here, these are, I guess, sort of sheet coverings. If you're working in an area with sort of large amounts of rainfall, what these will do is they'll keep the water from seeping into your slope and compromising its stability. But if you work in an area that's relatively dry, then you wouldn't really need to worry about that. So once again, project area or your site area conditions really sort of determine how you would design your slope. So in addition to the sort of soil you're working with, another key factor to take into mind or to take into account is a rainfall. Okay, so those are just a couple of examples of slope stability and when they're used and when you need to do the analysis. And what we'll have now is a very quick quiz. So the quiz itself is only 3 multiple choice questions. You'll have up to 5 minutes to. Okay, so part 2. Now let's talk about the limit equilibrium method. So during this section, I'll talk about its history, sort of the theoretical principles that govern it, analysis considerations, things to take in mind when you're using it, and then application for dams and embankments. Actually, sorry, this is a bit of a typo on my part. So the application for dams and embankments, which will be included in one of our later sessions. Okay, so let's talk about the development history of this method. So it is the oldest and most well-known technique for slope design. So for those of you who've worked extensively with slope stability analysis, this should be nothing new to you. It's been around for well over a century. It was sort of the first technique that was used or pioneered to analyze the stability of slopes. And because it's so old and so well known and recognized, it's currently the most widely used technique for slope stability analysis. And it utilizes something called the method of slices. So essentially, what you'll do is you'll take your slope and you'll draw what's called an arc failure surface. Typically, it's an arc failure surface, but there are certain instances where it's in the shape of a block or a wedge. I'll talk about that later. But if you remember the picture that I first showed you, slopes typically tend to fail with this sort of curved failure surface. So what you'll do is you'll create that arc tangent or that arc failure surface, and then you'll divide your slope into a series of slices, and then just using the laws of statics, you'll find all of the forces acting on those slopes, and then using those forces that you determine, you can determine the factor of safety or the stability of it, and we'll talk more in detail about it in just a minute. So initially, interslice forces were ignored. So interslice forces are simply just the forces acting between each of the slices. So for example, when I believe this slide here is slice here is highlighted. So because because it'll be sort of reacting, or it has a couple of neighboring slices here, there'll be a force in the normal direction as well as shear forces in the vertical direction acting on this slice. So previously, during the early methods or the early use of this the early sort of incarnations of this method, they ignored these interslice forces just because it was very sort of complex to take them into account. So certain assumptions were made. And also an iterative approach was necessary. So when this method first came out, what you had to do is you had to create sort of, you had to create your arc failure surface, and then you have to calculate the forces for each of your individual slices, and then you get your factor of safety. But what you'd have to do is you'd have to create a number of arc failure surfaces just because you didn't know whether or not you had your minimum factor of safety until you tried several iterations. So if you can imagine, engineers, what they would do is they'd have it usually on a board or a spreadsheet. They draw these arc failure surfaces over and over again, and they get the factor of safety for each one, and then use the minimum factor of safety for their design, which was something that was extremely time-consuming, very sort of detailed. But that was how it was done before the emergence of software programs. Okay, so let's talk more about its development history. So in the 1950s, 2 engineers or scientists, Bishop and Yanbu, finally considered the interslice normal forces. So this is typically called the Bishop simplified method or the Yanbu simplified method. As you can see, using the Bishop simplified method, the normal forces were taken into account. So what they did was they found a sort of way, or they derived a certain methodology where you could take into account interslice forces, and it wouldn't sort of complicate the analysis process too much. So that was sort of the first breakthrough in the limit equilibrium method. And then in the 1960s, computers made it possible to streamline iterative procedures. So for example, mathematically more rigorous formulations were then possible. So this led to the emergence of the Spencer and Morgenstern Price methods that include both interslice normal and interslice shear forces. So as you can see in the Bishop's method, the normal forces, they're considered, but the shear forces between each slices, they're sort of ignored. But because the emergence of certain computer programs, Spencer's and Morgenstern Price methods, which are very sort of repetitive and lengthy and complex to do by hand, engineers could then use these programs to take into account not only normal forces but also shear forces, which made designs much more optimized and much more accurate and reliable and much easier to do. So that's something that was really sort of made limit equilibrium method, or just slope stability analysis in general, much easier, was the emergence of these computer programs. It really sort of revolutionized how slope stability analysis was done. Okay, and now desktop computers in the 80s made it possible to develop commercial software packages based on limit equilibrium method formulations. So I'm sure you're all sort of familiar with these types of programs. For example, Slope W, Slide, Stable, and SoilWorks as well. They all have limit equilibrium method modules that allow you to just immediately or very quickly create your arctangents, set up your slices, and then find your minimum factor of safety. And in fact, you don't even have to calculate the interslice forces or the forces acting on your slices by yourself. A computer program will do all of that for you. So it'll actually create sort of a series of arctangents, and it'll perform the analysis over and over and over again based on this grid range. It'll isolate the minimum factor of safety for you. So something that would have taken half a day or maybe even 2 days for one engineer to do can actually be done within a matter of minutes by this computer program. So the main thing that you really need to sort of focus on now as a geotech engineer is really just to focus on the material properties that you're using, setting up your model correctly, and then analyzing your results correctly. If you can do those things, you don't really have to sort of worry about the sort of the details of the limit equilibrium method. The program takes care of that for you. Okay, so let's talk more about the theoretical principles, more specifically the method of slices. So the first thing to remember is that it's based solely on statics. So that's something that a lot of engineers, when they first learn about the limit equilibrium method, they're sort of surprised about. Because what typically happens is they'll start using these programs that they don't understand sort of the concept behind it. So when they realize that it's based purely just on physics, it's sort of a surprise to them because it's very simple and straightforward in that respect. So the limit equilibrium, or what happens is the forces act on a free body such that all remain stationary. In other words, the sum of all forces in the x and y directions and the sum of moments is equal to 0. So for those of you who remember what sort of physics class was like, essentially what they're doing is they're taking those laws, they're applying it to the slope stability type project or to these slices, and putting all of the sort of the sum of all the forces as well as the moments in equilibrium. And by doing that, you'll be able to find the forces that are acting on the slices to keep them in equilibrium. So the resulting computed forces may not represent actual field conditions. So this is another important thing to remember. So sometimes what engineers will do is they'll start, in order to get a better understanding of the limit equilibrium method, they'll go back to, they'll find these textbooks or they'll find these methods and they'll try doing a sample calculation by themselves, and they'll find that the computed forces seem sort of erroneously high or low. So the thing to remember is that that's actually sort of a normal thing. So in other words, the forces that you compute by hand don't actually mean these are the forces that are in the field. Because you're making certain assumptions, these forces may seem erroneously high or low, but that's not something to worry about. The main thing you want to need to sort of focus on is whether or not your factor of safety is within reason. Okay, and it's based on two factor of safety equations. So the factor of safety with respect to the moment and horizontal equilibrium, and this was first published by Spencer in 1967 in the Geotechnique article. So just sort of a recap of the factor of safety. Essentially what it is, it's just a ratio of the forces acting against your slope, sort of keeping it, making it unstable, versus the forces that are keeping your slope stable. So essentially, typically a factor of safety should at least be 1.5 or higher. So for example, try to imagine about 1 Newton of force that's maybe driving your slope to failure. So for every 1 Newton of force that's acting against your slope, there should be 1.5 newtons of force sort of keeping it stable. And obviously the higher factor of safety is, the more stable your slope is. Okay, so just to sort of go further into the method of slices, I won't go into each of these individual forces, but this I hope will help you sort of gain a better understanding, or anyway get a greater appreciation of what these programs do for you. So as you can see, there are all these forces that are taken into account when you're doing the limit equilibrium method. So you have, obviously the normal force, the force that's acting against the slope. You have some shear force along the bottom. You have interslice forces, both normal and shear. You have any sort of outside external forces. Those can be taken into account by the program as well. So all of these sort of forces, all of these angles, etc., need to be calculated in order to determine the factor of safety. Now, in order to determine the factor of safety, there's been sort of several equations that have been derived or that have been created that use these variables or they use these forces to generate your factor of safety. And the equations are as follows. So there are two main factors of safety that are determined, the factor of safety for the moment and the factor of safety for the force. So depending on the type of external force you're modeling, it'll be one of these factor of safety equations. But the main thing to sort of remember about these equations is that they've been derived based on they've been derived to use the forces that were calculated in the previous slide to generate your factor of safety. And another thing too important is that the normal force at the slice base is both in the denominator and the numerator. So back when engineers were doing these by hand, it was very important for them to get that value correct. Okay. So now that we've talked about the sort of theoretical background behind the limit equilibrium method, let's talk about sort of the modeling principles or slip surface shapes. So something that I alluded to previously was how, depending on sort of the type of material you're working with, the slope would fail in either an arctangent, or excuse me, an arc surface like this, a circular surface, or it could fail in sort of a block surface. So now when you're creating your model, there are certain sort of limitations that come when you create maybe like an arc failure surface such as this. So for example, if you're creating a circular slip surface or a circular slip shape, the interslice shear does not affect the moment, but it affects the force. Just try to imagine this circular sort of portion of your slope here as sort of the solid block or the solid piece. Now also imagine applying a moment, sort of a rotational force along maybe like the center here. What will happen is this block or this piece will sort of move along the shape of this curve without very much resistance. I mean, you'll get some shear forces or some friction forces along the bottom, but that can be taken as sort of negligible. And that's why if you look at the graph to the right here, as the interslice shear increases, the factor of safety remains the same. So regardless of the amount of sort of moment or rotational force that you apply to this, the factor of safety is not going to change. I mean, it's not going to meet any sort of resistance. Whereas if you were to apply a lateral force, sort of maybe a horizontal type force going against the slope here, this solid block, it wouldn't move along the bottom surface here. It would actually sort of press up against this area here. And it would meet a certain amount of resistance. And that resistance would increase as you increase the force or the shear. So that's why the factor of safety, as you can see here, increases as the shear increases. So that's another important thing to keep in mind is like when you're creating your slip surface or you're creating your shape, you need to keep in mind the type of force that you'll be applying to it because as you can see, if you're if you're doing sort of a moment type force or rotational type force, it's not really going to be accurately sort of represented here because the factor of safety is not going to change with any increase. Whereas if you're applying any sort of lateral or transverse loading, then this type of model would work well for you because, as you can see, the factor of safety is increasing, as it should. Okay, so let's talk about the next type of surface here. So this is called a planar slip surface. So as you can see, instead of a circular failure surface, it's just a straight line. It usually goes from the base of the slope to somewhere along the top of the slope. So if you look to the graph on the right here, the relationship has changed. So now, as we increase the interslice shear, or as we increase any sort of moment force, the factor of safety actually increases. So once again, just imagine this sort of portion here, this cut portion, is just a solid piece. Now, if you add any sort of rotational force to it, what will happen is there will be a certain amount of resistance that will increase from this this bottom portion here. So just imagine putting a rotation on it, or just imagine maybe like twisting with your hand this top portion. You're going to meet resistance, and as that resistance increases, so does the factor of safety. Now on the other hand, try just imagining applying a transverse or a horizontal load to this block or to this piece. What will happen is there'll be some resistance from the friction of the surface here, but what will happen is this piece will just sort of slide up. And that's why the factor of safety doesn't increase. So regardless of how much sort of additional force or transverse loading you add upon it, there isn't going to be a significant amount of resistance to show a change in the factor of safety. So once again, if you're working with a material type or it's a project type where you feel that you'd have more sort of moment force as opposed to shear force, then this type of failure surface might work better for you, or typically would work better for you. Okay, so let's move on to our next example. So this is called a composite slip surface. So just sort of at a glance, it looks very similar to the first example I showed you. The main difference, though, is that the arc failure surface extends beyond the base of the slope to sort of the flat level here. So let me go back here. So as you can see in my previous example, the circular shape or the circular failure surface, it ends at the very base of the slope. So that way, it's very sort of simple. It doesn't have to take into account the slices or any type of slices in this area. But what happens is when I take this area into account, there are certain changes that, or certain other variables that need to be taken into account. And this leads to typically, more accurate calculations actually. And this is actually the type of slip surface that was used by Spencer and Morgenstern Price when they were calculating or when they were taking into account interslice shear forces. So, it took more variables into account. It was harder to do, but ultimately it was more accurate. Because when a slope fails, typically there just won't be this sort of the part of the slope that's affected. The failure surface usually extends beyond the base. Okay, so let's take a look at what happens here. If we go to the right here, as you can see, the red here sort of corresponds to the moment. So if you put a rotational force upon this piece here, the factor of safety actually decreases. So the slope actually becomes less stable. This is because, because of these extra pieces here, there's more sort of rotation occurring and there's less stability. So that's another important thing to keep in mind. If you're putting a moment force on this type of slope, it's not very resilient towards it, and the factor of safety will drop sort of dramatically as you increase the moment. Whereas if you were to apply any sort of like lateral or transverse loading, the factor of safety would increase, naturally, just because, if you were to, there'd be a certain amount of resistance coming from this area here, keeping the slope stable. So that's another thing to keep in mind, when you're creating your slope models. Typically, it's a good rule of thumb to go a little bit beyond the base point, so that way you take into account this area here, because that's subject to failure as well, or subject to being a part of the slip surface. Okay, and now let's talk about block slip surface. So this is one of the more rare types of failure surfaces that are used, typically because it isn't really realistic for most of the soil types that are out there. So most slopes, they won't fail in a shape such as this. There won't be like these sharp corners here. Typically this is, when you have sort of rock types or sort of hard clay types, you might experience failure such as this. Or if you have certain fault lines, or pre-existing fault lines anyway, then your slope might fail in this fashion. But one of the things to sort of to keep in mind about this type of shape is that there's sort of an inaccuracy in the factor of safety calculations. So for example, if you were to take like sort of a normal slope where you would usually use an arc failure surface or a circular failure surface, and you were to use this type of failure surface instead, you could have sort of erroneously high factors of safety. Just because, since most soil types don't fail in this manner, you're essentially you're essentially calculating a slope that's more stable than it actually is, or that appears to be more stable than it actually is. So as you can see, as you increase force and moment, the factor of safety increases for both of them. That's because regardless of rotational or sort of lateral type of loading being applied, there's always going to be a certain amount of resistance sort of taking place or being applied from the rest of the slope here, from the soil layers. So because of these sharp corners here, the moment, regardless of any sort of rotational load you put on it, there's going to be a certain amount of resistance, as well as transverse loading. There's going to be, increasing amounts of resistance. So that's another important thing to remember, is that you should only really use block slip surface if you're absolutely sure that it's going to break in this type of fashion, or the slope is going to fail in this type of fashion. Otherwise, it's typically best to use an arc or a circular failure surface, because that's the natural way that slopes sort of break or fail. Okay, so let's talk about some application considerations. So there are a couple of shortcomings about the limited equilibrium method. First and foremost, it can provide stress to distribution and displacements. So if you want to sort of simulate the displacement of your soil as part of the slope, you can't calculate that, as well as any sort of stress in the soil elements. That can't be calculated by the limit equilibrium method. The main goal or the main purpose of using the limit equilibrium method is to calculate the factor of safety. That's pretty much it. So if you have like a very simple, smaller, straightforward slope stability type of project where all you need is a factor of safety, then usually the limit equilibrium method is your best solution because it's the simplest. Also, it is awkward to use for analyzing stability problems, such as the failure of cantilever and retaining walls, in which failure involves deformed wedges. So if you have any sort of more complex type structures involved, for example, if you have like it says here, like a retaining wall or any sort of cantilever, any sort of foundation by the slope, then it's very sort of awkward to use for those types of projects just because it can't sort of take those variables into account as well as the finite element method or the strength reduction method, which I'll talk about in the next chapter. And then unrealistic stresses for slices does not necessarily mean the factor of safety is wrong, so that's something I discussed previously. If you're doing the limit equilibrium method by hand, or if you're checking the forces acting on your slices, don't be discouraged by necessarily high or don't be discouraged by erroneously high or low forces. It's really the factor of safety that you need to focus on. You should not expect the computed stresses to necessarily represent the actual ground stresses. So, this sort of ties into the previous point here. The limit equilibrium method makes sort of several assumptions in order to calculate the factor of safety. So just keep in mind that the role or the main purpose of the limit equilibrium method is just the factor of safety. It isn't there to actually calculate realistic ground stresses. So any forces that you calculate, they're just being used to calculate the factor of safety. They can't actually be used. The computed stresses, anyway, can actually be used in a realistic design just because they're not the actual forces acting in your slope. Okay, and the limit equilibrium method is most commonly used as a simple solution method, but it can become inadequate if the slope fails by complex mechanisms such as internal deformations, brittle fractures, progressive creep, liquefaction of weaker soil layers. So just once again, keep that in mind. The limit equilibrium method is best suited for simple, straightforward projects where it's just, for example, self-weight or maybe small distributed or point loads. If you have any sort of complex mechanisms such as this, then the limit equilibrium method can't realistically account for them. Okay. So what we'll do is we'll have another quick quiz. It'll be the same format, 3 multiple choice questions. You'll have 5 minutes. I'll pull it up right now. Once again, just take your time. The questions are very simple and straightforward, so 5 minutes is more than enough time to finish this quiz. So here it is, and good luck. Viewing the quiz. So if that's still the case, just contact me afterwards, and I'll send you a copy of the quiz for your review. All right, so let's move on to part 3. So we'll go over now the strength reduction method. So we'll go over theoretical principles, considerations, and then we'll compare directly to the limit equilibrium method. Okay, so the strength reduction method, it utilizes Moore-Coulomb shear strength parameters, for example, modulus of elasticity, Poisson's ratio, angle of dilation, and tensile strength. And it uses these parameters to calculate the deformation and soil stresses, which I'll talk about more in detail later on. And it involves successive reductions by some factors in the shear strengths of slope materials until failure occurs. So something that the strength reduction method utilizes, it sort of utilizes these successive reductions. In other words, what happens is it increases sort of the forces acting on the slope until the slope fails. So what it does is it pushes the slope to its breaking point, and then it finds or calculates the minimum factor of safety from the forces determined. So this sort of method requires a lot more. If you're to do it by hand anyway, it would require much more amount of time and effort to calculate. But once again, because of the use of software programs that are out there, you can actually use the strength reduction method very efficiently now, and we'll discuss that in the final section. Okay, so failure is indicated when the finite element model does not converge to a solution because equilibrium cannot be maintained. So yeah, once again, that ties into this previous point here. What the program does, or anyway, what the method involves, is increasing that and increasing those stresses until equilibrium can sort of be maintained within the model, and then the factor of safety is determined from that particular case. And then the critical factor at which failure occurs is taken to be, the factor of safety. So, like I said previously. And then, depending on the basis of assumption for the failure strain, the shape of the critical section varies, and significant time is required for calculations by finite element analysis. So once again, this method, it's based on finite element analysis, or taking sort of a larger model, cutting it up into smaller pieces, and just using sort of integration to calculate all the forces that are acting upon it. It's a very sort of high-end way to do the analysis. And in order to do it by hand, it's a very lengthy process, even lengthier than the limit equilibrium method. But once again, just as engineers, using modern programs, the main thing to understand is just to understand what you're inputting into the program. So these will be your strength parameters, and then also understanding how the analysis is done, and then interpreting the results. So we'll be going over each of those in this section here. So even though we won't be directly discussing what exactly, the exact equations or theoretical background, or, in detail anyway, the theoretical concepts that are used for the strength reduction method. We'll just be gaining an understanding of sort of the process that's taken. So one other key thing to remember is that the failure modes vary depending on the modulus of elasticity. So this is one of your most important parameters whenever you're doing any type of finite element analysis. So one of the key strengths, obviously, of finite element analysis is that you can calculate deformations, which, depending on your project, could be a very sort of key result that you'll need in order to create a really optimized or economical design. So if you get your modulus of elasticity correct, then your deformation should be very close to what will actually happen in the real site conditions. So, for example, if this is just a sample of a 2D finite element model for a slope, and the calculation has been run twice. The only difference, though, is that in this model, the modulus of elasticity is much lower. So as you can see, as the sort of the way the slope deforms is very different. So each of these contour bands here, sort of the cooler the bands get, or as you go from the hot colors to the cool colors, the deformation or the magnitude of deformation decreases. So maximum deformation occurs, here, sort of along the face of the slope. But it also occurs, significantly sort of in the areas beyond the slope as well, or further away from the slope. But in this model here, the modulus of elasticity is much higher, so the slope, the materials anywhere are more resilient. So once again, deformation now only occurs sort of near the base of the slope here. So that's just a sort of a visual example of how much the modulus of elasticity can alter your results. So it's really important that you have your modulus of elasticity, if magnitude is in there correctly, and that you have it lined up with the right material. Otherwise, you could get erroneously high or erroneously low deformations. Okay, so there are certain factors that previously kept the strength reduction method from routine use. So let's take a look at them here. So, like I discussed previously, lengthy modeling, computation, and result analysis times. So even with early finite element programs, the computation times were, still arbitrarily long, up to the point where it was still more convenient to use a limit equilibrium method for smaller scale projects or smaller scale slopes. Then lack of automated tools for performing the successive changes to shear strength. So, without a sort of an automated tool or without an automated system or program to do, the iterative process of, doing your different cases for increasing shear strength, the analysis took, a very long time to do. That's obviously something that's been overcome now, but previously, before these tools were introduced, or before these programs were introduced, it took a really long time to create all those cases. And then a perceived hunger for material input data which were not collected in routine site investigations, at least not with reasonable accuracy. So something I discussed previously was that the modulus of elasticity, the Poisson's ratio, the friction angle, I think. Those were a couple of other sort of factors that needed to be taken into account. So previously, when the limit equilibrium method was still sort of the only real, legitimate or realistic option to use for slope stability analysis. The other material input data, such as modulus elasticity, etc., weren't really collected normally or regularly, so engineers had a hard time finding the data that they needed in order to perform the strength reduction method. Obviously, now the situation has changed. It's very easy, in the age that we live in now, to get that kind of information, or to get that sort of information about your site. Also, there was a restriction to linear material strength, or the more Coulomb material model. So, another reason engineers are hesitant to use this method was because they had to rely on the more Coulomb model to do it. Naturally, if you're not sort of experienced with a more Coulomb model, or if you haven't been introduced to it yet, you're sort of hesitant to try it out. But now the more Coulomb model is being more and more prevalently used. A lot more engineers are starting to understand how to use it. It's something that's taught very commonly in universities now. So once again, if you just understand the basics of the more Coulomb material model, you'll definitely be able to use the strength reduction method. And also the unproven reliability of shear strength reduction results. So the program or the method was still in its beginning stages, so a lot of engineers still didn't really trust the results they were getting. Obviously, now the situation has changed. The analysis method has been used a lot for a much longer period of time, and it's starting to become more regularly used, so the results are much more reliable and more trusted. Okay, so here are some analysis considerations. So these are some things to take into account or to keep in mind when you're doing the strength reduction method. So first, you should just assume a single Young's modulus and a single Poisson's ratio for the slope materials. So for example, if you have like a layer of soil, or a uniform layer of soil, you only need one Young's modulus and one Poisson's ratio for that entire layer. But if you have like sort of a layer below it of, say, weathered rock or weathered soil, then that would have its own individual Young's modulus and Poisson's ratio. So just keep in mind that if you have like a sort of a uniform layer of soil, then you don't really need to worry about having multiple Young's moduli or Poisson's ratios for them. Only one is really needed. I'll assign all materials elastic perfectly plastic behavior. That's pretty straightforward. Obviously, if you want to calculate the deformation, it's really important to assign it this type of behavior. And then use higher order elements. For a given number of nodes, higher order elements are generally more accurate. So for those of you who are new to finite element analysis, higher order elements just means sort of smaller, finer elements for areas that experience sort of high levels of strain or deformation. And that's something that I can show you a little bit better when we have the actual model. But when you're doing a slope stability analysis, it's really important to have higher order or smaller elements around the face of the slope, because that's where most of the strain and the deformation happens. Begin with a smaller number of elements, then refine the model or increase the number of elements once you've obtained a good handle on a slope problem. So once again, for those of you who are still new to finite element modeling, when you first create your initial model, what you want to do is you want to create a model with sort of larger element pieces. Another important thing to remember is that when you increase the number of elements, or when you make your elements smaller, the analysis takes longer to run, but the results are more accurate. So when you're first starting out with your model, obviously there's going to be design changes. You still want to maybe have a couple of other cases to compare it to. It's a good rule of thumb to use sort of larger elements, or excuse me, a smaller number of elements. That way the analysis can run much faster, and then later on, once you're sort of nearing your final design, all of sort of the changes have been, all the design changes have been taken into account, then you can run a more optimized, sort of detailed model. And then you need to check, excuse me, the sensitivity of results to the number of elements. So if you're using, high order elements along the face of your slope, then you'll be able to have results that are much more reliable. So once again, save the higher order elements, or anyway the very small or fine elements for your final design. That way you can have like an accurate, optimized design, or optimized model. Okay, then another note, the deformation parameters such as Young's modulus, Poisson's ratio, and dilation angle, these directly influence the magnitudes of computed deformations. So if at any point you feel like your deformations are erroneously high or low, it's always a good rule of thumb to just go back and to check the magnitude of these particular parameters, because these are the ones that directly influence how your deformation comes out. So more often than not, when an engineer, or when a model has an erroneously high or low magnitude of deformation, that just means that, it usually means anyway, that one of these values is sort of off by an order of magnitude, or it's been mismatched. So that's another important thing to remember when you're entering your parameters. Okay, so let's talk about how it compares directly to the limit equilibrium method. So first and foremost, it can more accurately simulate the behavior of support elements. So for example, if you have a slope with some tiebacks, or you have a slope modeled along a retaining wall, and you want to calculate the behavior of the support elements, so you want to get the actual strains or shears or moments of those elements, then you can simulate that very accurately with the finite element method. It can more accurately simulate interactions caused by the relative stiffness of slope materials. So once again, if you have any sort of soil structure interaction type projects, or maybe foundation to soil type interaction, you can accurately simulate that with the strength reduction method. That's something that actually can't be sort of factored in at all using the limit equilibrium method. It can indicate deformations of failure. So for whatever reason you want to simulate what your slope will look like or how it will deform, then you can do that with a strength reduction method. However, with the limit equilibrium method, as I said previously, the only thing that you can really calculate accurately with the limit equilibrium method is the factor of safety. With the strength reduction method, you can calculate the factor of safety in addition to behavior support elements, stiffness of slope materials, as well as deformations. So that's one of the key things to remember, is that with the strength reduction method, it's a bit of extra work to do, but you do have access to a wider array of results. Okay, so it eliminates the arbitrary assumptions regarding to the inclinations and locations of interslice forces. So with the limit equilibrium method, something that I stated several times is that the forces calculated for the slices don't necessarily represent real world or real life forces. So various assumptions are being made. However, with the strength reduction method, those types of assumptions aren't made. So any type of forces that you have calculated, interslice, or not interslice, but as far as interface elements, you may interface between certain soil elements or layers or support structures, all of that is meant to represent in situ conditions. Okay, and you can automatically monitor the developments of failure zones. So if you're running maybe a more in-depth analysis, if you want to, for whatever reason, monitor how the failure zone develops as more sort of strain or more force is applied to your slope, then you can monitor that directly with the strength reduction method. It's particularly useful if you're interested in the behavior of a slope over sort of an extended period of time. And it can be used to design support elements in a slope. So yeah, that sort of ties back. If you're working extensively in design, not just of the slope itself, but also of support elements or nearby sort of structural elements, then the strength reduction method can be used to help you design that in relation to the factor of safety. So if you have like a higher end or maybe a more complex type project where you not only need to calculate the factor of safety, but also need to do some design work for support structures or retaining walls or foundations that are around the slope, then the strength reduction method can really sort of streamline that process. So instead of having a separate sort of system to analyze the factor of safety, in other words, a limit equilibrium method, and then another sort of system or work process to do your design, and having to go back and forth between the two, you can just use the strength reduction method to do the factor of safety and your design. So it's very convenient in that respect. Okay, and then input parameters. So when you're using the strength reduction method, there are a couple of other input parameters that you need to take into account. So these are just the main ones here. So as you can see, with the limit equilibrium method, you have the unit weight, cohesion, internal friction angle. That's very basic. But with the strength reduction method, in addition to these three types of parameters, you'd also need the modulus of elasticity, the Poisson's ratio, naturally for calculating your deformations, and then also your drainage conditions for any type of seepage analysis that you want to run. So if you're doing sort of like a seepage analysis, that takes into account the slope stability of an embankment, then naturally you need your drainage conditions. So once again, that's another sort of shortcoming of the limit equilibrium method. I mean, you can calculate the sort of changes in water level, but as far as any sort of seepage analysis, you'd need to use a sort of finite element model to really get something more accurate. So for like a larger scale type seepage project, such as a levee, a dam, or embankment, then usually the strength reduction method is a much better option. Okay, and also the way that the models are created are very different. So with the strength reduction method, the model, what you'd have to do is you'd have to create a set of finite elements or mesh sets. So as you can see, there are three levels here, three soil strata, and triangular elements are used. And as you can see, as you go closer to the face of the slope, the size of the elements decreases. So there's more elements, but the elements themselves are smaller. So the reason this is done is because the smaller your elements are, the more refined or the more detailed your analysis is. So naturally, you'd want your elements to be smaller, or you'd want the analysis to be more detailed around the areas where you'd expect more amounts of deformation or more strain, etc. So as you can see, as you go closer to where that strain or that deformation occurs, the elements get smaller. Whereas if you go to the edges over here, or these areas, you're not going to experience much deformation or strain at all, so the elements can be much bigger. So that was what was meant in my previous slide about higher order elements. Higher order elements is just another way of saying sort of smaller elements to calculate more, to get more detailed analysis results. So also take note that you need to create boundary conditions as well for your model just to sort of simulate the forces, obviously, that are keeping this model in place. Whereas with the limit equilibrium model, what you'd have to do with modern sort of numerical modeling programs is you'd create a grid range here, as you can see, and then also, and it's a bit hard to see because of the color, but you'd create a number of arc failure surfaces. So each one of these arc failure surfaces represents a potential sort of slip failure surface for the slope to take when it does fail. And what the program will do is it'll take each of these points here and it'll link it up to a tangent or a point on that failure surface, and it'll create a series of slices for it and the factor of safety. So as you can see, it's something that would be very repetitive, done by hand, but what the program does is it does all of it very quickly. Within a matter of seconds, actually, the calculations are done. But just keep in mind that the main differences between these two are, you don't have to do any meshing with the limit equilibrium model. You don't even have to create any boundary conditions. It's just a matter of getting your geometry right, getting your material parameters right, and then creating like an accurate or an efficient arc failure surface in grid range. Okay, then more about the limit equilibrium model. So this is what the results section looks like. Typically, once the analysis has been run, the program will isolate your minimum factor of safety. So this grid range here, as you can see, these areas here in red anyway, represent sort of the critical range, or the critical sort of set of tangents where the minimum factor of safety is. So it's isolated the minimum factor of safety to this point here on the slope that corresponds to this tangent, and these are sort of this is your critical factor of safety, or excuse me, your critical failure surface with your minimum factor of safety. And with the program you can get all of the different forces acting on your slope as well, or all the different forces acting for each slice along your failure surface. Whereas with the limit equilibrium method, instead of just the factor of safety, which is calculated for you, you also get the displacement here. You get pore pressure, if you're running sort of a drainage system or different water levels. You get the effective stresses, acting on your elements or your soil elements. And then you'd also get your axial stresses for your any sort of tiebacks or any sort of support structures. So as you can see, just going back here, the factor of safety is 2.285, which is a bit higher. And then the factor of safety here is about 1.675. So just keep in mind, this is actually the same exact project, but done with both analysis methods. So another thing to keep in mind is that with the strength reduction method, or whenever you're running any type of finite element analysis, the results that you get are always going to be more optimized. So as long as you feel confident that you entered all your input parameters correctly and the modeling was done correctly, then the results that you get with the finite element analysis, or with the finite element method, you can have much more confidence that these are the optimized, or these are the most realistic results. So in addition to the factor of safety, you also get various other results which are especially useful when you're doing design work. Okay, so now what we'll do is we'll have the third quiz. Once again, it'll be 3 questions, 5 minutes long. What I'll do is I'll pull it up now. Take your time and make sure to click submit when you're done, and good luck. analysis. So for larger scale projects or higher end projects, it's typically used for those types of applications. That being said, it can also do conventional 2D analysis as well. The main difference is that GTSNX, it's geared towards sort of the 3D analysis aspect. Okay, so what I'll do is I'll pull up a sample demonstration. Let me pull it up real quick over here. Okay, here we go. So this is SoilWorks once again, and what I want to do is I just want to show you sort of the main sort of modeling steps involved when it comes to the limit equilibrium and the strength reduction method when you're using a numerical modeling program anyway. So for those of you who've done slope stability analysis before, you should have some kind of program. If not SoilWorks, then maybe Slope or Slide, one of those programs. So the interface is fairly similar. So one of the key things to remember is whenever you're using any sort of numerical modeling program, it's very important to get your material parameters correct. So let's check the ground material properties that we have inputted here. So if I open it up here, as you can see, I have 3 soil layers, but I have 6 material properties, each with 2 of these have the same name. So the reason I have 6 material properties is because I've run the analysis, or I've run both the limit equilibrium and the strength reduction method analysis. So as you can see, if I go over here, weathered soil, this corresponds to the more Coulomb material model, and it corresponds to, or it has all these different material parameters inputted. So modulus of elasticity, obviously it's very important for deformation, Poisson's ratio, temperature coefficient, etc. But if I go to weathered soil over here, LEM, I only have the unit weight, the saturated weight, the cohesion, and the friction angle. So as you can see, that sort of gives you, I guess, a better idea of the sort of additional material parameters that are needed for a finite element analysis. The same principle applies to weathered rock. As you can see, I have my various parameters that relate to deformation. But if I'm using the limit equilibrium method, I just have to worry about these 4 main parameters here. So anyway, in order to assign those material parameters, it's fairly simple. Typically what you do is you select the surface here, and then you just drag and drop from the material properties that you've created. Anyway, so let's focus on the limit equilibrium method for now. So let's say, for example, I have my slopes drawn here. I have all my material parameters assigned. Oh, and by the way, these lines right over here represent tiebacks, sort of keeping have been installed to keep the slope more stable. And material properties can be found for that as well. So as you can see, I have LEM properties for the soil nails or the tiebacks, as well as finite element properties. So if I go here, as you can see, I still need the modulus of elasticity, the Poisson's ratio, etc., yield strength I need. Whereas if I go to the limit equilibrium method, it's a much smaller sort of set of parameters. This is because with the strength reduction method, what I'll be doing is I'll be calculating the axial forces, the axial strain acting on these soil nails. So I need these parameters in order to do that. Whereas with the limit equilibrium method, I really just need to see how these soil nails or these tiebacks affect the factor of safety. I won't actually be analyzing what's going on with the nails themselves. I won't be analyzing their reactions. Okay. So now that I have my model drawn and I have everything sort of created, my next step would be to create my my grid surface, my grid range, along with my arc tangent or my slope failure surface. So if I open up this boundary here, as you can see, I've already created it. And if I sort of click on it, as you can see, each of these points corresponds to one of these arc tangents. And as you can see, it's the sort of circular slip surface that's used by Morgenstern Price. But if you want to create it, it's very simple. So let me turn this off real quick, and I'll walk you through the creation process. So just go here, and as you can see with this program, and with any other program really, you'll have the option to create a different type of failure surface. So you can create an arc failure surface, which is the most used, polygonal failure surface, or any sort of block or wedge failure. And then you'll also have several other sort of options that you can use, but the main ones are always sort of in the forefront. So let's go to the arc failure surface. And first thing you need to do is to draw a grid range. So typically when you're drawing your grid range, you just want to sort of put it like right over the slope. So it should start like near the base and end up sort of where the slope, or the steepness of the slope sort of comes down. So just go here. Typically, this is big enough. And then you can also change the sort of the increment of the grid spacing. So for more detailed analysis with a wider range of slopes, what you can do is you can increase the grid range accordingly. Oh, excuse me. Increase it like this. But typically, for a first run, it's good just to use sort of a smaller grid range or a smaller sort of spacing. Next, you need to draw your arc tangent. So you do so just by clicking this option here. And then usually what you'd do is you'd select a point here, starting at the base of the slope, to a point where the slope starts to level off. And then you'd click over here. And as you can see, there's 3 tangents. But if I wanted to increase the number of arc tangents, so if I wanted to, once again, increase the level of my analysis or the level of detail, I can increase that number. So anyway, once you create it, you can just click Apply in this case. And then you can check to make sure that your grid covers sort of the entire sort of length of your slope. So I guess when I did this previously, I made the grid range much larger, just so to make sure that I covered everything. So as a good rule of thumb, your grid range should, or anyway, your arc tangents, it should cover the range from the base or the point anyway extending beyond the base to where the slope levels off, which is what I've done here. Okay, so if it's not covering that area, it's just a matter of either redrawing your grid or moving it later. So anyway, once you create your grid range, you can just input, for example, if you're doing a case type analysis where you want to analyze the effects of the rainy season versus the effects of the dry season, what you can do is you can go here and you can assign a water level. And later on, as you can see, I've already assigned it to the top of the slope here. So this is like the saturated water level. So once you do that, what you can do is you can create a separate case, one with the water and one without the water. If I open this up here, as you can see, I have LEM saturated and then LEM unsaturated. So in one analysis case, I have the water level activated, and in this analysis case, I have it deactivated, just so I can see how the factor of safety is affected by that. So if I go to my results here, these are typically what your results look like. So here, you get your factor of safety right away. It isolates it for you. And if I turn it on here, as you can see, it corresponds to the grid range. So it's 2.855, and what I can do is I can double click on these slices here, and I can check what all of the forces are. So as you can see, the program does all of this automatically for you for each one of these slices. So it's very convenient, it's very detailed, and if for whatever reason you need these forces, you can just pull them up using this option here. I know SolWorks has this option, and several of the other slope programs should have this option as well. So that hopefully that gives you sort of a better appreciation of what the program does. And then if you open up this tab here, as you can see, the program, what it did was it did the factor of safety calculations for each of these failure surfaces. So as you can see, let's see how many exactly. Yeah, so it did this about 298 times, or it did 298 iterations, all within a matter of seconds. I know with LEM, the analysis itself takes less than a minute. So that's something that's really sort of beneficial about these software programs, or about numerical modeling in general, is that you can get very high-end or very sort of a wide range of analysis results. That previously would have taken many hours for a single engineer to do. So that's something that's very useful about it. And then also, if I go over here, let's take a look at LEM saturated, or unsaturated, excuse me. So as you can see, the water level here is represented by this blue water line. But if I go to unsaturated, as you can see, the factor of safety is now 3.4. So essentially what this is telling me is that the presence of water sort of greatly affects my factor of safety up to the point where it's, I think, sort of 1. It goes from 2.2 to about 3.4. So obviously, the slope is much more stable when there isn't water present. And for this particular arc failure surface, or this particular case, it went through the same process. It calculated all the factors of safety for all the different sort of points along this range here. Okay. Oh, and another thing to keep in mind is that when you're running your limit equilibrium method analysis, you'd want your minimum factor of safety, or the point anyway, to be located right near the center of the grid, or around the center. If it's all the way at the very edge of the grid, what it's telling you is that the program essentially ran out of space, and that this is the minimum factor of safety for that point. But the minimum factor of safety could expand to a point on the grid beyond that. So let's say, for example, my minimum factor of safety was along the very edge here. What I'd need to do is I need to go back into pre-processing and shift the grid up, then rerun the analysis until it was sort of near the center here. So that's another key thing to remember, is that the minimum factor of safety, the point should be right around the middle. If it's along the edge, you'll need to sort of shift that grid over. Okay, so that's just a basic rundown of the limit equilibrium method. Now let's talk about the strength reduction method real quick. So the way that the strength reduction method varies is first and foremost the use of, I showed you the different input parameters that are involved, but then also the way that you have to do the model is you have to create a mesh set. let me turn off this boundary here and turn on these mesh sets. So another important or key thing to remember about finite element modeling is that all of your material parameters are assigned to your mesh sets. So as you can see, this bottom mesh set here, let me open this up. So as you can see, each of these mesh sets is represented by a different sort of soil type or rock type. So soft rock represents this bottom mesh set. Weathered soil, represents this, or that top mesh set here, weathered soil, and the middle mesh set represents weathered rock. And also you need your boundary conditions here. And as far as just creating these, the modeling is very simple. Just go to geometry, or go to model here, and then you have all of your meshing options. And if I go to smart mesh even, it's just a matter, once you have your model created, you can just select the level of refinement for your meshing. So you can choose very fine or very small elements, higher order elements for your slope, and all the meshing will be done automatically for you. And then also, you input your sort of your water table, your water level. So that's sort of the main difference between finite element modeling and the limited equilibrium modeling. So with the finite element modeling, you don't even need to create a grid range. It's just a matter of creating your meshing and then putting your input parameters and your boundary conditions. So once you run the analysis, let's go to the results section here. Let's take a look at the results that are available to the strength reduction section. So if I go under SRM here and I open up this tab, as you can see, the factor of safety is about a 1.675, so it's more optimized, or sort of more. It's lower. So what it's telling you is maybe this slope isn't as stable as the limited equilibrium method says it is. And then also what I want to do is I want to take a look at my displacements. So let's open that up. We can get my vertical displacement and my horizontal displacement, as well as my total my total displacement here. And as far as finding out what these contour bands directly represent, you can refer to the legend here, or if you can go to results, you can go to this probe option here, and you can sort of see what your displacement is along a certain range. You can create a corresponding spreadsheet. Also, what's available to you is the sort of the embedded truss. So let's say, for example, I wanted to select a certain type, or wanted to design for a certain type of embedded truss, or a certain type of soil nail or tieback. What I need to do is I need to find the reactions for each of those cases. Now, with a limited equilibrium method, you can only get the factor of safety. But with a strength reduction method, you can also find out sort of what's going on with your support structures. So if I open this up, as you can see, I can get my axial stresses and my axial strains, my axial forces for each of these soil nails. So that's one of the main things to remember about the strength reduction method, is that you have sort of a much wider range of results available to you, and also ground element strains, etc., ground element stresses, poor water pressure. So everything here, all these things that aren't available in the limited equilibrium method are easily accessible to you in the strength reduction method. So once again, it really boils down to the type of analysis you're running. If you're strictly focused on just the factor of safety, then typically the limited equilibrium method will work best for you. But if you're doing any sort of higher level or any more sort of detailed design work, whether it be for the support structures or surrounding structures, or say you're building a retaining wall here, then the strength reduction method would be much more convenient anyway to be used for that design process. Because in addition to the factor of safety, you can get all the other forces or all the other sort of variables that are affecting the stability of the slope. Okay, so that's just a quick rundown of the limited equilibrium method and the strength reduction method via SoilWorks. But one thing that I want to bring up before we close is just the sort of how 3D modeling is done. So let me pull up GTS NX here. So this is a sample of a 3D slope stability model done on GTS NX, which is specifically for higher end or 3D analysis. So as you can see, if your slope isn't very sort of uniform in the lateral, or in the transverse direction here, as you can see, the slope is the way the contours are very sort of detailed or unique. Then sometimes just doing a simple 2D analysis won't get you the results as accurate as you would like. So as you can see, the way the contours change, the slope could be very sort of different for each one of these sort of, maybe if you take a certain series of cuts along the length of the slope here, the factor of safety or the forces anyway acting on them could be very different. So just using the 3D modeling aspect here, you can create contours that are very in-depth, very detailed. So for example, if I wanted to create maybe a detailed 3D contour such as this, it's actually quite simple if you have a spreadsheet representing all of your values. So let's say, for example, I want to create maybe a detailed 3D contour for the strata as well as the surface. So let's go back here, and let's let's turn the geometry off for now. Let's turn the meshing off. So let's say I want to import, maybe I have, my surveyor gave me sort of like a spreadsheet of all the different elevations for, a series of points along that, along the slope. What I can do is I can just use an option to import the surface for me. So if I go to this option here, and I type in, for example, let's say 50 by 50. So what this option does is it allows you to import a sort of a detailed contour from an existing spreadsheet. And the values that I'm entering are just sort of the parameters of that contour. So let me just set this up here, 270, 270. So what I'm telling the program essentially is that this particular surface that I'm importing, it has, the dimensions are 270 meters by 270 meters, and the increments or the grid spacing of each of those elevations is a sort of a 50 by 50. So it would be, 270 divided by 50. I don't remember what offhand that is, but that'll be, the spacing. Now let's say I want to import my elevation. I can just, this is what my spreadsheet will look like. So each of these values here represents a position and a z elevation. So the z direction is represented by, it's up and down here in the global coordinate system. So if I go to load, and I have, my text file, set up for me, what I can do is I can import them just directly into the program, and this will just take a second. And then, so these are all my different elevation values. And if I preview it here, this is what my contour will look like. So as you can see, within just a matter of seconds, you can have your contour. You can do the same thing for your strata beneath it as well. And then just using the modeling options here, you can create your slope. So for those of you who thought that maybe this sort of geometry is very difficult or very complex to make, it can actually be very simple if you have the right tools at your disposal. But in any case, let's focus on just the results for now. And let me turn off my geometry here. Okay. So as you can see, as I said before, the strength reduction method, what it does is it increases the shear strength over several sort of cases until it reaches failure, and then it generates your factor of safety. So as you can see, with the way the analysis was done, it did 11 iterations, increasing the shear periodically. And as it did so, the factor of safety increased, and then finally, the slope failed, and this was the factor of safety that was associated with that. So if you open up this option here, you get the same sort of options that are available to you in the 2D analysis. The only difference is now you can see them in 3D as well. So as you can, here's your total translation, your total deformation. So not only do you get the deformation at just one point along a 2D sort of area, you also get them along the full range of your 3D slope here. So as you can see, depending on where you are on the slope, the deformation increases. So naturally, these red areas here are the maximum or the critical sort of deformations, and you can see their sort of exact values by referring to the legend here. Now let's say, for example, I want to see maybe an exaggerated view of my deformation. So all I have to do is go to deformation, go here, go to deformation, and this factor is set to 1. So let's increase this to 2, and let's click apply. So here's sort of an exaggerated view of the deformation looks like. So as you can see, deformation, it sort of deforms or goes down, or compresses here, but then the slope rises over here. So these grids sort of represent the original shape of your slope. So this is something, that's obviously much more detailed, much more sort of in-depth as far as your analysis. But if you're having sort of a larger scale project where you need these types of results, then using a finite element tool such as this could be extremely useful too. And then also I have it here this is for the dry period, and I also modeled a rainy period as well. So what you can do is you can go case to case. You can see how deformation would occur during a rainy period and compare it directly. So let's take a look here. So as you can see now, because this is saturated, there's much more sort of uplift happening along this face of the slope, and then this sort of end area here is still sort of compressing. So that's something that you can do. You can have multiple cases for different water levels. You can get your factor of safety as well as displacements, deformations, etc. And now another great sort of sort of tool available in this program is, let's say for example you want to take a series of cuts just going along the side here. So let's move this back here, and then what you can do is you can use a clipping plane. So as you can see, the deformation sort of increases as you go towards the center. So let's say for example you want to take a series of cuts going along the length or along the sort of the y-axis here to show the different displacements as you go sort of further or closer to the center of the slope. So what you can do is you can just click add here, and you can create a sort of a series of slices to show how the deformation varies along different sort of areas or parts of the slope. So just click close. Turn this off. So as you can see now I have sort of a series of slices representing all my different or the different portions or different magnitudes of my deformation as I go down the length of my slope. And if I want to sort of get a range of results printed out, what I can do is I can just click on a certain range or a certain series of ranges, and I can create my spreadsheet like this. So this is particularly useful. Let's say for example, instead of having, if you were to do this purely in 2D, you'd have to create sort of 5 different models for each of these different sort of contours, which could be sort of very lengthy and time consuming. But if you have a 3D tool, what you can do is you can just create one model and you have all of your different slices available to you. So some other great options are you can, let me turn this off here, you can also sort of isolate certain areas or certain sort of magnitudes of value that are of interest to you. So as you can see, you can turn, using this option here, you can isolate certain, let's say you only want this particular range of values. You can sort of see where exactly those values are in relation to your model. Okay, and you can change it to the lower part as well. So you can see where exactly you have this level of deformation, where exactly it's going to deform. Also, if you just want to isolate certain ranges here, you can do the same thing with a clipping plane to have something much more detailed and in-depth to show different sort of areas along your slope where stresses and strains or displacements occur. So you can isolate these ranges, you can print them out. They're very sort of useful if you have a client that wants to see a very higher level of depth or detail for a particular project, or if you have like a larger scale project where results need to be very sort of in depth in order to sort of cut down on maybe project costs or to stay within budget. Then options such as these really help you to not only generate really great results, but also present them in a way that clients can easily understand and relate to. Okay, so that's just sort of the basic sort of outline of how numerical modeling can really help you out with slope stability analysis. I hope you found it useful. We're sort of running low on time, so I can't go into too much detail. But if you have any further questions, feel free to contact me, and I'll do my best to answer any of your queries. So now let's just wrap up here. So this concludes session 1. The next session will take place 2 weeks from now on March 12th at 3 p.m. Eastern Standard Time. The topic of discussion will be pile foundations. So we'll go over PY and finite element analysis. So similar to this lecture or this session, we'll go over conventional analysis type, PY analysis, and then we'll also go over finite element analysis, and we'll compare the two, and we'll discuss how each of these analysis types can be used, and the sort of the strengths and weaknesses of each. And just like with this session, I'll give at the very end, I'll give a quick numerical modeling demonstration to go over how the modeling is done and the different results, how they can be extracted using numerical modeling programs. If you have any questions, feel free to give me a call or to send me an email. I look forward to the next session, and I'm definitely open to any of your feedback. If there's something that you'd like to see in the following session that you haven't seen in this session, just let me know, and I'll do my best to meet your needs or meet your desires. Thanks again for your time. I hope you found this useful, and just keep in mind that a recording of this session will be posted later on. So if maybe you want to show this recording or share this with a couple of your friends, we'll send you the recording and you can view it for free online. Okay, so once again, thank you very much for your time and attention. I hope you all found this useful, and I'll see you on March 12th.